We now have Khaled Daher joining us, who'll be presenting us this very relevant topic. Khaled will show us how EVs and electric trains are reshaping the future of city commuting. He'll help us understand the impact of EVs and electrical trains on urban planning, the importance of charging infrastructure, and the benefits of transitioning to electric mobility for environmental sustainability as well. Khaled is Installation General Manager at CAF. He's also a member of the faculty board here at Ziggurat, teaching on our master's program in smart city management.
Yeah. So appreciate your time, and would like to present a presentation about EVs, about electrical trains today, which are part of smart mobility. So we'll go to the first slide. Yeah, let us start about how do electrical vehicle work, or what does it mean? So I have a short video for you just to explain about EVs, just to make the topic is interesting in the first.
Ever wondered how EVs get from A to B? Is it essentially the same as an internal combustion car, but wired up to a giant battery? Or is there some altogether more subtle trickery afoot? Join us today as we pop the frunk and ask, how exactly do electric engines work? Surprisingly, the operating principle behind most modern electric vehicles predates the internal combustion engine by a number of decades. In 1834, a Dutch professor named Sibrandus Strating of Groningen, Netherlands, built his own small electric vehicle. The catch being, its battery was non-rechargeable. Internal combustion engines work on the principle that fuel and air, when compressed and ignited, cause a tiny explosion. That's the combustion part. This explosive force pushes a piston. That piston's linear motion, in concert with a team of fellow pistons, transforms into rotary motion via a mechanical crankshaft. This in turn spins your wheels along the highway. Conversely, the fundamental principle that drives electric cars is magnetism. Everybody knows how opposing poles on a magnet attract and how alike poles repel each other. So let's imagine an experiment using two magnets, one fixed, the other mounted on a nearby rotating shaft. If the two poles nearest to each other on both magnets share the same polarity, say north to north, the magnet on the shaft will be repelled. Because it's attached to a shaft, the shaft will turn. That is until the south pole on the shaft magnet is aligned with the north pole on the fixed magnet, whereupon the shaft will again be still. In our imaginary experiment, we've made the shaft turn a half rotation. All very well, but that won't get us very far on the morning commute. Here's where electromagnetism enters the chat. In a fixed or permanent magnet, like the kind you have on your fridge at home, those magnetic poles are rigid and never change. North is always north, south is always south. On an electromagnet, however, which is essentially a core of metal coiled in electrical wires, this magnetic polarity can be reversed. Imagine one of our experimental magnets is now an electromagnet. If the south pole quickly flips over to north, the fixed magnet will yet again repel the moving magnet, rotating our shaft another half spin. That's a whole spin now. We're slowly getting there. For a basic illustration of how this polarity reversal works, imagine a very simple circuit involving a battery and a light bulb. Electrons flow in one direction from the battery, through the wires, to the light bulb, and back again to the battery. If we remove our battery from the circuit, flip it 180 degrees, then replace it in the circuit, those electrons will still flow around the circuit, just in the opposite direction. Either way, the bulb lights up. Electromagnets, like light bulbs, work whichever direction the electrons are flowing. But rather brilliantly, the polarity of the magnet gets reversed with the flow of electrons. So to keep our magnets in permanent repel mode, we just need to keep reversing the polarity of the magnet. How do we do that? One way would be to keep popping out the battery and flipping it around. But that's a lot of trips to the mechanics with your EV for the sake of a few feet of ground covered. So the real trick to making our magnet spin, which is essentially how electric motors work, is through the so-called inverter. The inverter module on the EV draws direct current from the car battery and, through a clever combination of quick switches, slick circuitry, and capacitors, flips the flow of electrons back and forth nearly 60 times a second. Domestic electric motors, like the one you have in your hairdryer, don't require an inverter. Why? Because the current that comes from your wall outlet already flips back and forth. That's why it's named alternating current, or AC. Batteries of any type can only ever produce DC, or direct current. So spinning magnets driven by alternating current passing through coils of wire is essentially what drives electric cars. Electric powertrains have a number of advantages over the internal combustion engine. For starters, the motion produced by the motor is already rotary in nature. Dirty pistons on an ICE require a complicated breakable crankshaft just in order to turn their linear motion into rotary movement. So EVs are less likely to fail or require expensive, time-consuming maintenance. Here's another clever thing about that inverter. By adjusting the frequency and amplitude of its newly created AC current, the vehicle's speed and torque can be finely calibrated by its driver. There's no such fine control built into an explosively hot internal combustion engine, which is why expensive and accident-prone additions like gearboxes are a tiresome necessity. Another nifty detail about any EV's powertrain is when the shaft-mounted magnet, or rotor in engineering parlance, is itself spun, it generates electricity. This reversal very handily recharges the car battery. How can the rotor be turned, you ask? With any hefty source of kinetic energy, like, say, a braking automobile, which is handy. This is, to be clear, a very simple overview. There's different types of electric motor, and refinements to the design are happening all the time. Not least at one particular Californian car company named for the 19th century genius who discovered the magic of alternating current by himself, Nikola Tesla. What do you think? Will your next vehicle be an EV? Let us know in the comments. And don't forget to subscribe for more. Ever wondered how EVs get from A to B?
Okay, so after the first video, we'll talk now in details about how our electrical trains are shaping the future of city commuting. So we'll talk about the first point, environment impact. We'll talk indeed, I'll show you next slide, a video about environment impact, and the second point about efficiency and reliability. And the next one is, next one about reduce noise pollution. And the fourth one, integration with renewable energy. And the last one is infrastructure development and capacity. For sure, about environment impact, it's a challenge for all the countries now to reduce the emissions and to produce fewer CO2, reducing air pollution, and to be aligned with the climate change and enhancement. About efficiency, they offer for sure AV and electrical trains shorter travel times, increase faster acceleration. About noise, electrical trains or AVs, we can see that there's no noise at all. Even starting with the electrical trains now, there is noise barrier to maintain that, to ensure that any noise comes out of the train. About the next point about renewable energy, we can use the solar cell, we can use wind turbine, we can use different options of renewable energy, which are part of smart cities also. About the last point about infrastructure development and capacity, investment in electrified rail lines, and it creates jobs and increase transportation capacity to accommodate growing urban populations, which is most important point. Now I'll show you a short video about environment impact for the all diesel train, which is disaster. You can see this video. It's really, it was a very old solution, and now with electrical trains, now a big difference. We cannot see any CO2 or any emissions, so we are aligned with the climate change improvement. Now, again, we'll talk about the impact of AVs and electrical trains on urban planning, which is the main core for this presentation. We'll talk about infrastructure development. For sure, urban planners must develop supportive infrastructure like charging stations, electrified rail lines, rectifier rooms, how we can develop, and how we can ensure that no one will suffer about from where he can charge his vehicle. The second point about land use. Planning needs to consider that space allocation for charging infrastructure, mixed use development near the transit hubs, near the transit station, and walkway also to be a friendly walkway for friendly environments. The next point about transportation networks. Planners must optimize transportation networks to accommodate electrical vehicles and train as much as we can, including dedicated lanes and smart traffic management system. Now, recently in such countries like even developed or developing country, they started to put specific lanes for AVs, specific lanes for the cars, sharing cars, even for the buses. And the next point about environment consideration. adoption of AVs and electrical trains can reduce pollution and emissions. If you remember in the previous slide, how the diesel train was, with emission of CO2 and pollution, it was catastrophe. So about environment consideration, we can talk about influencing urban planning strategies towards sustainability. So this is an important point about this is revolution. And the last point about accessibility. It's essential to ensure that equitable distribution for electrical transportation infrastructure to all communities, poor, rich, black, white, old or young. So all of them, they have the same level of transportation and will be have, it's fair for all of them. Also addressing of barriers to adoption like cost and accessibility also. I will show you the impact also for electrical vehicles, how we can also maintain that to be charged in the duration, a very short duration. So for example, this short video show us how the buses can be charged in short time. By the way, this is the duration for charging is around 30 seconds, so it's nothing. So you can see the bus, drop in, drop, and the people get in, get out, and at the same time the buses are getting charged in 30 seconds. So this is it's a good duration. It's something it's challenging also. And the benefits for transition to electrical mobility for environment sustainability. For sure, we are talking now and previous on the countries now, they are talking about emission reduction. Electrical vehicles significantly reduce harmful emissions, CO2, CO1, and improving air quality and public health. So we can say, I cannot live in this country because a lot of pollution there are no fresh air. So I need to go to villages, I need to go to cities. Now with AVs, we can live, all of us, in the smart cities with health condition. The next one, climate change mitigation. Absolutely lower greenhouse gas emission contribute to combating climate change and reducing transportation sector's carbon footprint. And the next point is about energy efficiency. Electrical vehicles, EVs, are energy efficient, leading to reduced energy consumption, promoting sustainable resource use and recycling. And all this one is, according to sustainability principles. And the next one, promotion of renewable energy. As we mentioned before, we are talking about solar cell, about solar energy, wind turbine. As we mentioned many times, solar sun is free for all, so we can use this advantage. And then the last one, noise reduction and resource conservation. AV contribute to noise reduction, as we mentioned before. Also require fewer natural resource of operation, enhancing over environment sustainability. Now, we talk a lot and we have seen videos about EVs. I would like now to talk about electrical train. So the interesting engineering behind electrical train. I have a short video to show you about electrical train. The principle, if you remember 3 slides before, how it was the emission from diesel train. And this will show you an electrical train, clean energy.
It might be surprising to know that in electric trains, the power collected from the overhead lines ends up in the grounding cable of the track after flowing through the wheels. 3-phase power conversion, regenerative braking, and zigzag overhead lines. All these make electric train technology quite unique. Let's understand all the engineering secrets behind the electric train, starting from the simplest design possible. The simplest version of an electric train is shown here. Here, a single sliding wire collects electric power from the overhead lines. This power is fed to a single-phase induction motor. The induction motor's rotor is connected with the wheels. To complete the circuit, the induction motor's other terminal is grounded. This grounding connection is possible because the wire is first connected to the wheels through an axle brush. The wheel is always in contact with the track, and the track is grounded, as shown. you can see how the current from the OHL flows to the ground. It first passes through the induction motor, then the axle brushes, then the wheels, and finally to the track and ground. When the current passes through, the induction motor's rotor spins, along with the wheels. However, a spinning wheel will move forward, which means the next grounding circuit should be available at a very short distance from the previous one. Now, let's look at some axle brush details. The axle brushes are fitted to the rotating wheel, and the current is transferred to the wheels through these carbon brushes, which slip over the disc attached to the wheel axle. Again, this is the simplest version of an electric train. Now, let's improve this design and make our train more functional. The voltage used in the overhead line is 25 kilovolts, which is a huge voltage. Motors require much less voltage to run. For this reason, we need to feed it to a step-down transformer, which transforms the voltage to the desired level. The power supply from the overhead line initially passes through the transformer's primary, and here, the circuit is completed due to the grounding. Because of the transformer's action, the current will be induced in the secondary winding and reduced voltage power is fed to the motor. For high traction like the train, the motor should supply a high torque. Moreover, the torque curve should be uniform, even if the motor speed varies. Three-phase induction motors are the perfect choice to achieve high, uniform torque requirements. Stretching three-phase wire to power this motor is not a good idea, as it's highly uneconomical. That's why a rectifier and inverter is used to convert the single-phase supply to the three-phase supply. A rectifier converts the single-phase AC power into DC power, and then the inverter converts the DC power into three-phase AC power. Now this engine is ready to run over the track. We can increase the torque output further if we add a transmission system with some gear ratio between the motor shaft and the wheel axle. At this point, the engine we just made seems perfect. However, if we make a complete train by connecting several coaches to this engine, it becomes quite clear that the single motor engine we developed doesn't have sufficient power to pull all these coaches. So, let's add more motor wheel pairs to make the engine more powerful. An engine bogie is constructed with three-phase induction motors, obviously to drive 3 pairs of wheels. In an engine, generally 2 such engine bogies are used. In this complete engine, you can see how the transformer and rectifiers are positioned. So far in this video, we've shown how we transfer power to the train using a single hanging wire. However, this method is not practical. Sometimes it is not possible to keep the distance between the train and overhead line the same, which means for proper power collection, a height-varying mechanism should be used. Pantographs accomplish this task. A modern pantograph looks like this. You can see that based on the pressure of a pneumatic system, the pantograph can adjust its height. If you observe carefully, you can see that during this height adjustment, the current collector remains horizontal. The current collector has to be perfectly horizontal. Otherwise, power transmission will be in trouble. We hope from this animation you can understand why the current collector always remains horizontal. For more details of it, please watch our detailed video about the pantograph. Now, let's see the pantograph in action.
So I will cut this video here just to be aligned with the time Chris give us. What do you think, Chris?
It might be.
So I'll talk about smart mobility can prove to be cost effective in the long run due to several factors, because I have received a lot of questions about smart mobility. It's worth to implement it in the countries, in the smart cities. Yes, the answer is yes, because I have many reasons there. You can see here, smart mobility can prove to be cost effective in the long run due to several factors. Efficiency gains, smart mobility reduce congestion, travel times, and fuel consumptions, yielding long-term cost saving for individual and business. Imagine that every day, 3 or 4 million trips have been reduced because the people they started leaving the car and using the smart mobility, public bus, trains, metros, AVs, also sharing cars. So it's efficiency gains. The second point, infrastructure optimization. We need to remember that technologies like intelligent traffic management extend infrastructure lifespan and minimize the need of costly expansion or repairs. And the next point is reduce externalities by curbing emissions and congestion. Smart mobility mitigates negative environment and health impact, resulting in a significant long-term societal savings. So our health now is in the good direction. And the next point, data-driven decision-making. Data analytics optimize the transportation systems, reducing waste, and thus saving costs. All these points, it's saving costs for us also. And the last point, PPP, we can say public-private partnership, collaboration, leverage resources effectively, sharing cost and risk to achieve mutually beneficial outcomes. And these all the points can answer the question: smart mobility save money and cost effective? The answer is yes. The last slide will be about a small video about EVs again.
So, electric cars. Really? How? When? Where? Everywhere? Yeah, you better believe it. The future of driving will be powered by plug-in. Across the world, countries are implementing bans on the sale of new petrol and diesel cars. For example, in the UK, the deadline is 2030. In Canada and California, it's 2035. And that is forcing the hand of the auto industry to make some big changes. Billions of dollars are going into creating greener vehicles. And some of the biggest manufacturers in the world are buying into this electric revolution. The trail is already being blazed by the likes of Tesla, and there are new kids on the block too. So, yes, buying electric is the future, but that doesn't make the future green. Not yet. Much of the electricity needed to power that trend is still generated by fossil fuels, exactly what we're trying to get away from. Clearly, there's little point in plugging in your electric car to recharge its battery using dirty energy. But as power grids become greener, it will become easier to charge up sustainably. Before that, though, they have to get the charge up to speed. A Tesla, for example, can supercharge about 180 miles of range in 15 minutes. But even that is 5 times longer than it takes to fill up with petrol. The good news is there's massive investment in battery research right now, leading to ever-increasing power and charge. But the next big challenge is rolling out sufficient charging points for the hundreds of millions of electric vehicles that will be quietly humming around in the coming years. There's something else, though. Batteries need rare earth minerals like lithium and cobalt to work. But current mining practices in places like the Democratic Republic of Congo are associated with human rights abuses such as child labor, and they often create pollution. So, supply chains must be transparent to ensure that the minerals mined for the batteries are sustainably and legally sourced. And a circular economy has to be developed so that materials are reused and recycled rather than continually extracted. But most of all, we must make sure the developing world does not get left behind in this revolution and just become a dumping ground for old petrol and diesel cars. Bottom line, there's a long way to go, but we know where we're going and we're heading in the right direction.
So the slides are over, guys. Do you have any question?
Thanks, Khaled. That was really interesting. I do have some questions, obviously. The first one is about electric trains. I know you've been involved in some electric train projects in different parts of the world, but I'm also conscious that electric trains have been around for quite a long time, as have electric tram systems and trolley buses in cities. You know, I grew up near Zurich, and Zurich has had an electrified public transport system for a very long time. So on the one hand, there must be a lot of data available in terms of cost effectiveness and things like that. But also, I wonder about innovation, like how much. Obviously, it's quite mature, but is there still a lot of innovation going on in this area? Is there still, the modern systems, are they a lot different from the systems that I grew up with 40 years ago?
Well, okay, for railway, we can say in general, railway now, there are a lot of innovation now. We can start from the old school diesel engines. After that, they have switched to catenary system, which is a electrified system. And now the trends about battery train. So now will be the first tramway in the world in Saudi Arabia will be installed without any power sources, only in battery system, which is the most advanced system. So you can imagine that you cannot see no wires, no electrification system for visibility, for look and feel. It's only battery system inside the train. So the rail and the train tramway. So you can see where the innovation comes with. And they will install also renewable resources, renewable energy resources like solar cells, renewable energy. And all this innovation now, you can see the difference between diesel engine and renewable energy for the train. So all of this one, it's make cost effective for sure.
Okay, so that battery driven system, when is the battery charged? Is it overnight, or is there wireless charging en route, or what?
It will be in a station. So, but in interstations, no any charge. So in station, it will be there is a charger will be installed there.
So it every time it stops at a station, it's topping up the charge.
Yeah. Okay. So it's nothing, because the dual time for trains to stop in the station around 1 minute or 2 minutes depends on the passengers, and in the 1-2 minutes we can charge the train.
Right. So tell us about some of the projects you've been involved in. Where were they, and what kind of systems were installed?
Well, I have been involved in a Riyadh Metro project, Cairo monorail. Currently, I'm working in Jerusalem LRT. And I was also designing phase for Copenhagen, Denmark, and all of them clean energy railway, no more diesel. All of them, we could talk about third rail, catenary systems, and hopefully my knowledge will be expanded also to see the battery system railway.
Mm-hmm. Actually, Copenhagen is a good one because, one of the benefits obviously is noise reduction. And I think this is true. Copenhagen introduced a ban on combustion engines for construction work last year or the year before. I don't know if you're aware of that, but reducing noise pollution as well as emissions is a big deal, right?
I can mention something about noise pollution because, as mentioned in the beginning of the slides, we are installing also noise barrier where we have a lot of homes, a lot of, for example, university hospitals. On the track, we are installing noise barriers to maintain that no any noise coming out of the train. So we can ensure that the people, they can sleep well, the university can go smoothly for education without any new noise pollution. So it's also something of innovation for the railway.
Yeah, great. It also strikes me that, like with smart cities, obviously we're measuring a lot of things that we didn't measure as much before, and obviously noise sensors, emission sensors, pollution sensors. We now have a lot more data, and our cities are transforming as well. So a lot of our city centers are now, less driven by retail and people going into the city centers to shop, and a lot of cities, certainly in Europe, are transforming into being more residential, and schools are being built in city centers again for the first time in quite a long time in some cities.
Absolutely.
So do you think that the rationale is just getting stronger for electric power trains in cities because of the amount of data we're collecting on these other factors?
I can answer this question with one example. During the construction of railway, also we are ensuring that the noise pollution is very less. So, for example, if we are building electrical trains or during the construction phase in city center, we need to maintain that the people around us, who is living around us, they are not, getting frustrated or exhausted because of the construction works. You can imagine if we are caring about the noise during the construction. So the final solution of the railway should have no any noise at all. And this is part of the contract with any government. So they said, okay, for example, noise should be maximum 2 dBs or 10 dBs or 100 dBs. So they define for us how many decibel for us to the final solution will come. So if any pollution, noise pollution will not come from AVs, even not from electrical train. It will come maybe from another sources, not from our smart mobility sector.
Right. And you're compiling the data for that. You're actually sensing it so you can prove the fact.
There are some sensors. We're installing some sensors about microphone, just to like noise sensors also. In case, like in airport, for example, there are noise sensors in the airport. When we have any platform of the airport, some noises, the speakers will go up for the sound. So any people, they can hear the sound of the platform, the train is coming. In the city center also same. We have noise sensors in each platform.
Right. Just finally, final question before we leave you. Obviously, the electric drivetrains, electric public transport are going to be disrupted by automation and autonomous vehicles as well. So where do you see that connection between EVs and autonomous? Where's that going? Where is it at the moment? Is it going to be a big cost saving? Is it going to enable things that don't exist at the moment?
Well, okay, driverless metros now started to be in operations. For example, in Dubai, there are driverless. In Paris also. In Riyadh Metro, it's a driverless metro, no driver at all. It's called of automation of Go 4. So no driver inside the train. And interfaces with the roads, and to make sure that autonomous vehicles to be a part of this smart mobility is highly recommended and started. Okay, for example, in the junctions in the city center, when we have the road junctions or the cross junctions, we are installing also sensors where with the traffic lights. For example, if the train will cross the sensors, all the traffic lights will be red. It will be likewise also for the AVs and autonomous vehicles. When we have specific lanes in the beginning for autonomous vehicles, it should be communicating each other with the train, with the walkway, also with all the traffic signals there. So it's the interface between them. It's high, and all of them should be in the same software, same control center. So right. no any conflicts, no any gaps between them.
Yeah, so a big interconnected system, all monitoring itself and every vehicle within it.
Exactly. So for sure, it will require a lot of investment about it, but it will happen. It will happen as we have driverless trains now is working in the world, so it will happen this one. Yeah. And it's opportunity to be invested for all of us and about the research.
Awesome, thanks so much. It was a really clear account of what's going on in EVs generally and in city mobility. So really appreciate your time. Thanks so much, Khaled, for joining us.
Thank you, Chris, and all the best. And I'm sure next time we'll have more initiative and more ideas, smart ideas.
Yeah, absolutely. Let's do this again.